Hello, everyone. This is going to be AP Chemistry Unit 6 notes, part 3 and 4. So the first thing that I'm going to start off talking about is solubility equilibria. And we're going to define solubility first and foremost, which is the amount of a substance that will dissolve to form a saturated solution at a particular temperature. So mostly in this class, we're going to deal with salts, so ionic substances. And the solid salts are going to form an equilibrium with their dissolved ions. So what I mean by that, to draw that out, would be, let's say we're dissolving sodium chloride in water. So that would form an equilibrium, it's solid, with its dissolved ions. And both of those would be aqueous. So for any salt, you can write out this equilibrium, and we can define exactly how much of any particular salt will dissolve using KSP, which is known as a solubility constant. So I know that we have a lot of different K values. So far, I think we have KEQ, KC, we have KP, and now we have KSP. Realistically, a lot of these K values mean pretty much the same thing. The little subscript really just tells you what is being given respect to with these K values. So for instance, Kc is an equilibrium constant with respect to concentration. Kp would be with respect to pressure. And in this case for Ksp, our equilibrium constant is with respect to the solubility product. All right. So if we're going to talk about the solubility of any particular salt, in terms of that KSP, if a salt is soluble, so on our solubility rules, all the ones that say soluble next to them, they would have a KSP greater than 1. And if they are insoluble or partially insoluble, they are going to have a KSP value of less than 1. So let's talk really briefly about why that is. We know that K values are defined as products over reactants. So if we look at that equilibrium that I just drew out again, NaCl in equilibrium with its ions, our products are going to be these two over here. And they're going to go on the top and our reactants go on the bottom. So if our KSP value is big, that means that a lot of ionization is happening, right? That means that there's a lot of products there. So that would make sense to have a big K value if there's a lot of ions present. So soluble salts would have a lot of ions present. Whereas something that's not very soluble is not going to have a big concentration of those ions and therefore would have a smaller K value. To compare insoluble salts to one another. So here, you are going to be tempted to just compare their KSP values to one another. So you're going to look at salts and go, oh, this one has a bigger KSP than that one, so it must be more soluble or less soluble or whatever. Don't do that. And the reason for that is that not all salts are equivalent to one another. There's sodium chloride, which has a 1-to-1 ratio. But sodium oxide has a different ratio, right? So Na2O versus sodium nitrate, Na3O, or sorry, N. So that ratio of one ion to the other is actually going to influence the value of our KSP, which means that you cannot directly compare KSP values to one another. Instead, you have to compare what we call S values or molar solubility values. Molar solubility is defined as the number of moles of solute that can be dissolved per liter of solution before the solution becomes saturated. So molar solubility is very similar to regular solubility. It's just that regular solubility is determined in terms of grams and molar solubility is in terms of moles. So really that's the difference between them. As for how you come up with those values, that's going to be from ice tables. And I know we all love ice tables. So here's an example. We have lead 2 chloride here. So there's our solid lead 2 chloride, and that's going to be in equilibrium with the lead 2 plus ion and 2 chlorine ions. So if we want to know what its molar solubility is so that we can determine how much will dissolve, etc., we want an ice table. Now, we know that we leave anything that's in solid state or liquid state out of an ice table, right? So this doesn't matter. The amount of solid still left in that does not matter in terms of our KSP. So for our salts, for our KSPs, you're going to notice that there's not really a denominator there because our reactant is in solid form. So that's why it's left out of this ice table. Now, if you dump solid lead 2 chloride into water, initially, at the moment of addition, you're not going to have any dissolved ions, hence our initial concentration of 0 for our lead 2 plus and our Cl1 minus. Then, as that substance dissolved, we are going to get an addition of concentration S and 2S for our lead and our chlorine respectively. And again, this is 2S because of this little 2 right up here in our equilibrium equation. Then at equilibrium, our concentrations are going to be expressed as S and 2S because we started out as 0. And we can define our KSP as equivalent to our concentration of our products over reactants, right? So that would be our Pb2 plus times our Cl minus, but that's squared because of that 2 here. Theoretically, it should be over PbCl2, but again, that's a solid, so we're going to actually not put that in our KSP expression. And when we plug in values in terms of S, we get this here, S times 2S squared for a 4S cubed. So overall, we get our KSP is equal to 4S cubed when we work out that math. Now, if we have a value available to us for KSP, as the problem is telling us right here, we absolutely can solve for the molar solubility or S value of that ion. So we would take 3.2 times 10 to the negative 4th, plug it in for S cubed, and solve for S. So S is going to be equal to the cube root of 3.2 times 10 to the negative 4th over 4. And I'll leave that up to you to work out what exact number that is. Because I know that even though we super love ice tables, sometimes they can be tedious, there is this very helpful table that allows you to not do an ice table every single time you have to figure out a molar solubility. So if you have a salt that has a 1-to-1 ratio of cation to anion, so silver 1 chloride or calcium sulfate would be an excellent example of 1-to-1 ratios. Your molar solubility can be determined by S squared. So you would have your KSP is equal to S squared for anything that has a 1-to-1 ratio of cation to anion. If you have a 1-to-2 ratio of cation to anion, your KSP value is equal to 4S cubed. Now, one thing to pay attention to, it is going to be 4S cubed no matter if you have a 1-to-2 ratio of cation to anion or if you had a 2-to-1 ratio of cation to anion. 1-to-2 or 2-to-1, either way, it's going to be 4S cubed. Now your 1-to-3 is going to be 27S to the 4th. And again, that could be 3 cations to 1 anion or 1 cation to 3 anions. And then a 2-to-3 ratio here yields 108 times S to the 5th. And that could be 2 cations to 3 anions or vice versa. So if you don't want to do an ice table every single time you figure out a molar solubility, just memorize that table. So we are going to do a sample problem real quick. The solubility constant of PbI2 is 7.10 times 10 to the negative 9th. Write out the equilibrium reaction and the equilibrium expression for that salt. calculate its molar solubility, and then calculate the solubility in grams per liter. So if you want to do this by yourself first, go ahead and pause the video here and I will address it in just a second. If you have no idea how to start, stay with me. All right, so to start out this problem, we have our salt that is a 1:2 ratio of cation to anion. So we can say that our KSP value, our solubility constant, 7.10 times 10 to the negative 9th, is equal to 4s cubed. Now, if we solve for s, that's going to be our cube root of 7.10 times 10 to the negative 9th over 4, which gives us a value of approximately 0.00121 moles per liter. So you can also write that as a capital M for molarity. So again, that's the amount of moles of this particular salt that can dissolve in every 1 liter. So just looking at that value, we know that lead to iodide is not particularly soluble. So that answers B. I know I did this a little bit out of order. So let's address A really quickly. Write out the equilibrium reaction and equilibrium expression. Well, our equilibrium reaction is going to be our PbI2 in solid form, which is in equilibrium with our Pb2 plus in, that's aqueous, plus our 2I minus, again, aqueous. That's our equilibrium reaction. Our equilibrium expression is going to be KSP is equal to products over reactants, except we're leaving our reactant out because it is in solid state. So we have our concentration Pb2 plus times our concentration of I minus squared. All right, now letter C. That's calculate the solubility in grams per liter. Not as difficult as it sounds. We already have our solubility over here in moles per liter. So we just have to convert that mole value to grams. So we set up our T-chart, 0.00121 moles per liter over 1. To convert that to grams, all we have to do is find our molar mass of PbI2. And our PbI2 molar mass is approximately 461, adding up 1 lead and 2 iodine. So we're going to get a value for our grams per liter solubility of approximately 0.559 grams per liter. So if you have any questions about how I did that, please don't hesitate to ask me in class. Moving on. We have another sample problem. Which of the following salts has the highest solubility at 25 degrees Celsius? So this temperature, really all that it's telling you is that these different salts are not at different temperatures. When they are all at the same temperature, we can go ahead and do our math and not worry about any changes in temperature. Our first step for this problem should be to identify our ratios of cation to anion. So magnesium hydroxide has a 1:2 ratio. Silver chloride has a 1:1 ratio. Barium carbonate has a 1:1 ratio. And finally, this last funky looking one has a 1:3 ratio. So consulting our table, we can go ahead and fill out our S expressions without having to do an ICE table for all of these. So skipping ahead a little bit, I went ahead and filled out the table. Once we solve all of our expressions, and we do that again by equating KSP to our molar concentrations expressed in terms of S, we get solubility values of these following 4. So to pick out the salt that has the highest solubility at 25, all you have to do is look for the biggest value. So immediately, both of our 10 to the negative fifths are out because 10 to the negative fifth is a smaller number. Then we get these 2 negative fourth values. This one is the highest value, indicating that the most amount of this particular salt over here can dissolve in 1 liter of solution at 25 degrees Celsius. So this would be an example of a multiple choice style question that they might give you on the AP exam, just wanting you to compare these S values to one another real quick and pick out your most soluble salt. moving on, determining if a precipitate will form. So this piece of information here over on here is very important. When you are comparing QSP and KSP, so remembering QSP and KSP are equivalent at equilibrium, but if you are not at equilibrium and QSP happens to be smaller than KSP, that means the solution is unsaturated, there are not enough ions present, and no precipitate is going to form. If QSP is bigger than KSP, then the solution is oversaturated. There's too many ions present, and the reaction is going to shift to form that precipitate. So once again, remember that every salt that's dissolvable has an equilibrium, right? So our PbI2 formed an equilibrium with its dissolved ions. So if our QSP is bigger than our KSP, that means our reaction is going to shift to form that solid, shift to the left. If our QSP is smaller, that means our reaction is going to shift to the right and favor more dissolved ions. So our sample problem says, will a precipitate form if 0.5 liters of a 0.25 molarity solution of potassium chloride is slowly added to 0.5 liters of a 0.25 molarity solution of lead 2 nitrate? Our KSP for that particular salt is 1.6 times 10 to the negative fifth. So once again, if you don't have any idea how to start, stick with me, but if you'd like to attempt this on your own first, go ahead and pause the video here. All right, so the first thing we want to do to solve this problem is we want to understand what's going on. So our problem states that we are adding a solution of KCl to a solution of PbNO3 2. So let's write that out chemically. KCl plus PbNO3 2. Now, looking at that, that looks like a double replacement reaction to me. We have two compounds reacting. We are likely going to form two other compounds. So if you remember your reaction patterns, we know that the first will bond to the last and the two middles will bond together. So we're going to end up with potassium nitrate and, sorry, it's weird, lead chloride. All right, so if you're unclear as to how I got those two compounds, I just did my reaction patterns and then swap and drop. So out of our two products, potassium nitrate, that is soluble. Nitrates are pretty much nearly always soluble, especially with a group 1 cation like that, which means that this one here has to be our at least partially insoluble product. And so we know that that partially insoluble product is going to form an equilibrium with its dissolved ions. So that's going to be Pb2 plus and 2Cl minus. Okay, so now we know what's going on. So our problem asks us if a precipitate will form if this much KCl is added to that much potassium nitrate. So now we have to start doing a little bit of math. Okay, so I'm going to go ahead and rewrite everything. I'm going to rewrite our equilibrium up here. PbCl2 is in equilibrium with Pb2 plus and 2Cl minus. And I'm going to erase everything down here. Okay. Next, to know anything about what's going on, I have to create a QSP expression and I have to compare that to my given KSP, right? So I know that my QSP should be equal to products over reactants, except this is solid, so just our product concentration. So our Pb2 plus times our Cl minus concentration raised to the second power because of that coefficient right there. So that's what I'm shooting for. So ultimately, I need to know what my Pb2 plus and my Cl minus concentration are. Well, I'm given some information about that here and here. My Pb2 plus concentration is going to be equal to the concentration of my PbNO3. And I know that because in every PbNO3 molecule, there is only one lead. There's only one Pb there. So as this dissolves, my PbNO3, my concentration of that whole molecule is going to be equivalent to my dissolved ion. My KCl, well, that's going to be the same story for my Cl minus ion, because as this KCl dissolves, there's only one Cl molecule for every, or only one Cl ion for every KCl molecule. So my Cl minus concentration should be equivalent to my KCl concentration. And if that weren't the case, you would multiply or divide by whatever number you needed. Now, again, we want to know these concentrations after addition, so after every single thing has been mixed together. So we need to do an M1V1 equals M2V2 for both of these concentrations here, because we are given concentrations before mixing and we want to know after mixing. So we're going to treat this concentration and this volume for each as our M1 and V1. So for lead, that's going to be this one and this one. We have an M1 of 0.25 molarity times a V1 of 0.5 liters. And it's going to be the same story for our KCl, 0.25 molarity and 0.5 liters. Now to get our our concentration after mixing for both of them, we have to consider what the total volume is going to be after mixing. We're mixing half a liter of one thing with half a liter of another thing. So our V2 for both of these is going to be 1 liter, and we are solving for what the concentration of each thing is in both cases. Now, when we work this out and we solve for M2, we get M2 of our Pb2 plus is equal to 0.125 molarity. And we get the exact same thing for our Cl. Why did we get the same thing? Because our initial additions were the same molarity and the same volume. So, taking that information, we can now plug this into our QSP formula that we already wrote out. So our QSP is going to be equal to our lead concentration, which we solved for, 0.125, times our chlorine concentration, which again we solved for, raised to the power of 2. So overall, it's going to be 0.125 cubed, which if we do that math out is equal to 0.0020 approximately. Now 0.0020 is much bigger than 1.60 times 10 to the negative 5th, which is what our original KSP value over here is. And since our QSP value is bigger than our KSP value, that solution is oversaturated, meaning that a precipitate will form. So that's very long, but that's how you answer whether or not a precipitate will form in a partially soluble salt solution. All right, once again, if you are unclear about where I'm getting my numbers, please ask me in class. Moving on, we're going to talk about part 4, which is again acid base in equilibrium. We're going to start out by talking about the common ion effect and how that affects the solubility of certain salts. So our common ion effect is used to describe the effect on an equilibrium involving a substance that adds an ion that's already part of that equilibrium. So if you want to visualize that real quick, there is a diagram right here. So we have SrC2O4, and that forms an equilibrium with its 2 dissolved ions. Now, if we add something with the same anion or cation for that matter, if we add more things to that equilibrium system, that's going to throw off the equilibrium. And we already talked about what can happen using Le Chatelier's principle. So in this case, we are adding Na2C2O4. Now it's going to split up into our sodium ions and these ions over here. Now, our common ion between both equilibrium systems is this one. So if we add more of this ion, we're adding more product to this equilibrium system, and that is going to shift our entire reaction back towards the precipitate, right? Because you're adding more of that common ion, and you're going to overall reduce the solubility of your original salt because you have shifted the equilibrium towards the precipitate. So that is our logic-based look on how that works. But unfortunately, it's not only logic-based. You might see an actual numerical value, or the AP test might ask you for an actual numerical value. So that's why we have this mathematical approach. Now, if we do an ice table for the dissolution of this solid right here, we would get that overall our KSP, which is given, is equivalent to S squared. And we would get a molar solubility value of 4.0 times 10 to the negative fourth. So remember, that is because our KSP is equivalent to S squared. And I know that because our cation to anion ratio was a 1:1. And so whenever that happens, we can see the KSP is equivalent to S squared. This ice table is just here as a proof to show you how we got there mathematically. So this is alone without the addition of a common ion. This is our molar solubility value. However, if we add something else, we are changing the initial concentration, right? So our ice table is going to look a little bit different. If we add this here, NaC2O4, we're adding more of that common ion. And we know exactly how much we're adding because we're told, hey, we're adding 0.02 molarity of NaC2O4. We know that that's going to ionize into Na plus and C2O4 2 minus. Ooh, this should be a 2 right here. That's a typo. So we know that we have an extra concentration of 0.02 molarity here initially because we're adding something else. So in our ice table, when we add and get our equilibrium concentrations, we have a known value. So we can still say that KSP is equal to S squared, except now we have a value for S. It's not just unknown, right? So instead of S squared, we have S times 0.02. And I know that it is 0.02 because our KSP value is really small. So this addition of S onto our 0.02 molarity is going to be so insignificant that this equilibrium concentration is basically going to be equal to 0.02. And we call that small s or small x approximation. So when we plug this into our KSP expression, we get that our KSP is equal to S times our now known equilibrium concentration. And when we solve for S, we're going to get this number down here. We're going to get that S is now equal to 8.0 times 10 to the negative 6 for our new molar solubility. And if we compare that to the molar solubility we got before we added a common ion, it is smaller, and we can see that mathematically. So this is a proof saying that our molar solubility has decreased by this amount when you've added a common ion. We also have to talk about how pH affects solubility. Some salts are going to be sensitive to pH changes, which means that an increase or decrease in the pH of the solution that contains that salt can affect how much or little of that salt is dissolving at any particular time. So looking at what happens, we have salts that can be defined as basic salts, or we have salts that can be defined as acidic salts. Basic salts are going to be more soluble when you make that solution acidic, whereas acidic salts are going to be more soluble when you make that solution basic. So there's a couple of things to know for that. If you have a salt containing the chloride ion, bromide ion, iodide ion, nitrate, sulfate, or chlorate, those are going to be excluded from this slightly soluble basic salt rule. So they are not going to be more soluble in acidic solutions, but something containing hydroxide or the conjugate base of a weak acid would be more soluble in an acidic solution. So basically, unless that salt contains an anion that comes from a strong acid, it's probably going to be a basic salt. If something is an acidic salt, it needs to have a transition metal that has a charge of +2 or higher, or a main group metal that has a charge of +3 or higher. So let's take a look at an example here. Will the molarity of the cadmium ion increase or decrease with the addition of a hydroxide containing base? So let's look at this, for example. If we add more hydroxide into this equilibrium system, we add more hydroxide, and that's what a base containing hydroxide is. We're adding more product, right? So that's going to shift our equilibrium to the left. So our addition is actually going to make that particular salt less soluble, not more. But what if we performed essentially an opposite shift? What if we instead tried to dissolve the same equilibrium system as above, but in an acidic solution instead? Well, if we have a bunch of these H3O pluses in solution over here, and we're trying to see how that affects the solubility, well, H3O pluses are going to immediately react with our two OH minuses, right? Because positive and negative ions are going to interact with one another. And when those two things interact, H3O plus and OH minus, they produce water. They produce water. And so what you're doing there is you're getting rid of one of the products. And so the reaction is going to shift to compensate for that, actually creating more product and increasing our solubility of that cadmium ion. And that concludes our notes part 4. So if you have any questions on anything that I just said, please make sure to ask me about it in class.